Start this video with a visual example of a piecewise continuous function, and then I'll give an example of a function that's not piecewise continuous. So, for instance, on the interval from a to b, we could have a function that does something like this, and then it's continuous here, and then there's a jump, and then there's another continuous part, and then in between it's defined as this value right here, and then maybe we have something like this, another jump discontinuity, and then a piece that is continuous. So this is a piecewise continuous function. Like the name says, it consists of continuous pieces of a function, and it only has so-called jump discontinuities. Now, a function like this, from a to b, that has maybe something like a vertical asymptote and looks something like this. This is a function that is not piecewise continuous. Because instead of a jump discontinuity, there's actually an infinite discontinuity. So as long as you have finitely many of these jumps, you're fine, but you cannot have an infinite discontinuity or infinitely many of those jumps. Then the second definition that we need in order to state or give sufficient conditions for when the Laplace transform exists is the definition for exponential order alpha. A function f of t is said to be of exponential order alpha if there exist positive constants, capital T and capital M, such that the absolute value of f of t is less than or equal to m, capital M, times e to the power alpha t for all t greater than or equal to capital T. So I'll give an example of a function that's of exponential order and then one that is not. So for instance, if you look at f of t is 4e to the power 5t times sine of t is of exponential order 5 because when you look at the absolute value of f of t, that's the absolute value of 4 times e to the power 5t sine of t, which can be written as 4 times e to the power 5t times the absolute value of sine of t. So what I'm using here is that the absolute value of a times b is the absolute value of a times the absolute value of b. And I can do that with three factors. So absolute value of A times B times C is the absolute value of A times the absolute value of B times the absolute value of C. So when you take the absolute value of positive 4, that gives you 4. The absolute value of e to the power 5t is just e to the power 5t because the exponential function is always positive. And then we take the the absolute value of sine of t. Now, because sine of t is always between -1 and 1, we can actually write this as that this is less than or equal to 4 times e to the power 5t times 1. Sine can never be bigger than 1. So if you compare that with a definition, we actually see that the definition is satisfied with m equals 4 and alpha equals 5. So we can use this as m, and we can use that as alpha. And so it's of exponential order 5. Now, let's do an example of something that's not of exponential order alpha. So g of t, let's say, is e to the power t squared, is not of any exponential order. Because no matter what value you take for alpha, this exponent grows linearly. It grows like t, whereas this exponent grows quadratically. So there's no way that we can pick an alpha so that this function can be bounded by this expression, the absolute value of that. So anything that grows faster than e to the power alpha t is not of any exponential order. And basically, we need that because we want the indefinite integral to converge. And if e to the power negative st times f of t grows too fast, the integral will not converge. So this is summarized in the following theorem that gives sufficient conditions for the Laplace transform to exist. So if f of t is piecewise continuous on the left closed interval 0 to infinity and of exponential order alpha, then the Laplace transform of f exists for s greater than alpha. I will conclude this video with one more example of finding a Laplace transform. And so I want to point out that when I do a Laplace transform on the exam, it will be of this form. So it will be a piecewise defined function, because the other Laplace transforms you can just look up in a table, and I want you to be able to find a Laplace transform of something that you might not be able to look up in a table. So this is something similar to this will be an exam problem. So similar to. Okay, so when we do the Laplace transform, because we cannot look this up in a table, we start with the definition. So the Laplace transform of f of t is going to be equal to the indefinite integral from 0 to infinity, and then f of e to the power negative st times f of t dt. And because f of t is piecewise defined from 0 to 3 and from 3 to infinity, right, we can think of this as less than infinity. So we have 0 to 3 and 3 to infinity is what we need to split our indefinite integral. So the first part is from 0 to 3. And then we have e to the power negative st. And on that interval, the function's given by e to the power 2t. And that's dt. And then we add to that the integral from 3 to infinity. And then we get e to the power negative st times our function there is 1. So that's times 1 dt. So now let's evaluate that. So I'm going to simplify this to e to the power 2 minus s times t. And so when I take the antiderivative of that, I get 1 over 2 minus s, and then e to the power 2 minus s times t. And then I have to evaluate that at 0 and 3. And then what I'm adding to that is, and I'm going to introduce a limit there. The limit as n goes to infinity of the antiderivative there. The antiderivative is negative 1 over s e to the power negative st. And I'm going to evaluate that at n, and the other part is 3, because the second integral went from 3 to infinity. So the first part is just substituting in the correct values, and so that's e to the power 2 minus s times 3. And then minus 1 over 2 minus s, and then e to the power 2 minus s times 0. And then plus the limit as n goes to infinity of minus 1 over s e to the power negative s times n. And then minus minus, right? Minus negative 1 over s e to the power negative s times 3. Okay, the first term becomes 1 over 2 minus s, and then e to the power 6 minus 3s. The second part, we plug in 0 here, and then we get 1. And so I could just leave the answer as minus 1 over 2 minus s, but typically we write it as 1 over and then s plus or minus a value. So I'm going to write this as a plus and then distribute a negative inside the denominator and get s minus 2. And then and this is 1. And so for the next part, this limit is going to be 0. So if you do everything right, that limit will typically turn out to be 0. You just have to say when that happens. So if negative s is less than 0, and that's equivalent with s being greater than 0. So that is 0. We can ignore that as long as s is greater than 0. And so the last part then is plus 1 over s times e to the power negative 3s. And so this holds for s greater than 0. And this is almost our final answer. One thing that we have to keep in mind is that we have 1 over s minus 2. And so when s equals 2, this Laplace transform is not defined. So one thing we also have to have here is that s is not equal to 2. And if we actually have to define an interval, so not a union of intervals on which the Laplace transform exists, we can combine this as the Laplace transform is valid on 0, 2, and then 2 to infinity, and then the biggest interval on which it's valid is 2 to infinity.